record this class. Yeah, Roy, you need to work harder. I think Jack got the highest grade, and the highest grade is 85, which really surprised me and startled me. Okay, but now I understand why. If this is your last mathematical class, so that's okay. Yeah, Jack, I agree. That's why I took out 4. I took out 4 questions. Right, 4 questions having typos. All right, okay, thank you. Anyone has questions? Anyone has mathematical questions? Okay, Jack, if you do what you are doing, you have no problem to pass. If your grade is lower than, yeah, it's basic, it's graded out of 100. You're right. Yeah. All right, so let me try. So if anywhere you feel confused, because I don't know how to speak a perfect English, all right, so I'm sure I always confuse you. So whenever you feel confused, please ask me, all right? Please ask me. And I was not born and raised in America. I was born and raised in China. So my English has a heavy accent. I understand that. So if I ever confuse you, you don't think you understand me, ask me, I'll try. And also, maybe get some help. It would be great if we could get the practice questions before the final. What do you mean practice questions? So your homework, your homework is your, so all those questions are chosen from your homework set. Just some numbers changed. But the only problem is I did not try every question myself because I thought, okay, the question comes from the exercise. So every question should be right, should be, but then I forgot, you know, textbooks always have typos, always. So for final, I'll do better. For final, I will choose from your homework set. And also I'm gonna do it myself first to make sure there's no typo. Get extra credit. Just work on your final, okay? Work on your final. I think I make the final. Right? I was not told the final comes from the department. Let's see, if the final comes from the department, you know, I would get to know before you know. So I would give you practice exam. I would give you practice questions, all right? Oh, sure, Paul. If you see some typos in the questions in the homework, right? Just ignore it, just let me know. You know, this homework, this number doesn't make sense. Okay. Yeah, I think life is so busy. You know, textbooks nowadays have so many typos. It's just unbelievable. When I studied, when I was a student, rarely I find, you know, typos. Okay, any other questions? All right, so we are studying sequences. Okay. We said sequences can be represented with a set notation, you know, set notation of such ANs. Then there's a pattern, especially we learned two typical sequences. One is called arithmetic. Arithmetic means in between of two terms, there's a constant difference. The distance is constant. And we call arithmetic sequence. Okay, here, right, arithmetic sequence, like this sequence, 3, 7, 11, 15, 19. We could take any two numbers in the neighborhood, two numbers, like 3 to 7, difference is 4, add 4, 7 to 11, adding 4, so on and so forth. So we can represent an in terms of previous one, which is previous one plus n. And ideally, we can represent the nth term as a function in terms of its position. Okay, so n is the number of its position in the sequence. Right, let's see this one. This one, n starts with 1. So 1 times 4 will be 4, 4 minus 1, 3. That's the first term. That's A1. That's A1, 3. Then 7 will be 2 times 4 minus 1. Right, A minus 1 is 7. So sequence like this is called arithmetic sequence. So what is it? It's a linear function, right? It's a linear function. We could think f of x equals to 4x minus 1. So arithmetic sequence, usually we can represent as a linear function. And the constant change is the slope, right? And the second famous sequence is called a geometric sequence. Geometric sequence means the neighborhood, the two numbers next to each other, and the next two numbers with each other have the same ratio. So basically, from first term to second term, from second term to third term, from current term to next term, we just multiply by a same ratio. And normally we call it ratio R. For this one, we see 2 times negative 1/3 give us as the second term, negative 2/3. Then multiply by negative 1/3 again, that give us 9/2, so on and so forth. So we see they have a common ratio. So arithmetic, they have a common difference. Geometric sequence, they have a common ratio. Right? So also we can represent it like this. The nth term equals to negative 1/3 of the previous one, of the previous term. And if we do further, we see we can, because they have common ratio, we can think almost like exponential functions. But the exponential function, the base has to be positive. The base cannot be negative. But in sequence, the base can be negative. So that's the difference. That's the beauty about sequences. That's exactly the reason why, you know, we want to construct a sequence more than a function. If everything can be represented by a function, we don't need to create other structures. So this base, it looks like exponential functions, but this base can be negative. So we have some examples, right? So A and B in this case, we see A can be, okay, we see, okay, the first one is negative, second one is positive, the third one is negative, so we call this the alternate sequence. So negative, positive, negative, positive. Usually we use negative 1 raised by n. Especially for this one, the first one is negative 1, negative. So we started with A1, n equals 1. We started with n equals 1. So the first term is a negative, so we have negative 1 raised by n. If the second term, if the first term is positive, second term is negative, we probably do negative 1 parentheses n plus 1. So the first position would be negative 1 squared. The first one would be positive. So the second one, we compare, then in the end, we can, the nth term can be written as 3 raised by n divided by 3n plus 1. So basically by observing the pattern, right, the pattern for the numerators, we see that is 3 raised by 1, 3 raised by square, so on and so forth. And the bottom, 4, 7, 10, 13, we see the common difference is a 3. So that's a linear function, so exponential over linear, right? Numerator is exponential function, denominator is a linear function. So recurrence relations. So let's say A, we have a first term 2, then the current term equals to -3 multiplied by the previous term, starting from the second term. So, but usually we're starting from the second term when we write a recurrence relation. So this one we can write out a couple of terms. In the end, we see that the 2 multiplied by -3 raised by n minus 1, right? It's like an exponential-like, because the base is negative, so it's not exponential function. The second one, we write out a couple of terms, right? Then we observe the numerator, so this is read as an equals to 1 minus 1 over 2 raised by n. Again, exponential function, right? So this one is exponential function because the base is 2. The base is 2. And we talk about the limit of sequences. So we want to know, where does the sequence heading for? Does it converge? Does it diverge? Converge means the sequence, comes to a number, approaching to a number. And diverge means the sequence approaches to infinity, doesn't converge to a number. Because sometimes the sequence can be represented by a function, so the limit of the sequence is just the limit of the function, and we see the sequence converges. The limit law just follows by functions, follows exactly the same as the functions. Because why? Because if it converges to a real number. Anything applies to real number, it applies to limits. Let's see this example. We want to determine convergency and find the limits. So we take a limit of A. We see that approaches to 5, right? Because limit of 3 over n squared when n approaches infinity, that goes to 0. And B, well, let's do from here. Right. So limit of 1 over n squared is 0. So when we take a limit of 5 minus 3 over n squared, that's just 5. So this is very similar to the functions, right? The second one also very similar to the functions because B looks like a rational function. So we take a limit. So limit when n approaches infinity, we just take the leading terms in the numerator and leading terms in the denominator. What do we get? We get -3 over 4. -3 over 4. Okay, even we write it in sequence form, but because it looks exactly like a function, so it's just the same as a function. C is different. We see with 2 raised by n and n squared. Well, we know that's not a function. So we take a limit, x approaches infinity, 2 raised by x over x squared. What do? We use L'Hopital's rules. Because 2 raised by x, when x goes to infinity, that goes to infinity. X squared, when x goes to infinity, x squared also goes to infinity. So we have infinity over infinity as indeterminate form. So we could apply L'Hopital's rule. Right? Apply L'Hopital's rule. Then again, then in the end, we see it approaches infinity. So we conclude the sequence diverges. If the sequence doesn't converge to a number, converges to infinity, that means the sequence diverges. So y equals the limit x approaching infinity, parentheses 1 plus 1 over x, then raised by x, That's the definition for Euler number, E. So when the numerator inside the 4 is 4, so we could do the calculation. But the calculation is kind of a strategy. But since only Paul goes to vector calculus, so you need to really remember this. So this is one of the mimics in mathematics. So how do we take a limit of this form? Involve the E term. So limit of x approaching infinity, parentheses 1 plus 1 over x raised by x. That's the definition of Euler number. Okay, so how do we take a limit of this? We take a log, natural log on both sides. Because the natural log and limit can switch. So which means we can pull the limit out of natural log. All right, so we take a natural log of the inside first, because we want to pull the x in the exponent down to base. So we go through this process. In the end, we get the limit equal to e raised by 4. E raised by 4. So actually, that gives you a hint. That gives you a hint. So this form, just a definition for e raised by 4. As you can imagine, if 4 change to be 5, that's e raised by 5, so on and so forth. Right. Okay, I think that's. Okay, let's see this one. Limits involving continuous functions defined on convergent sequences determine whether the sequence cosine 3 over n squared converges. If it converges, find its limit. Because cosine is a periodic function. Right? Periodic function, we know it jumps from -1 to 1, up and down, up and down. So we take a limit of this cosine by 3 over n squared. The good thing is we can switch limit and cosine. So limit of cosine equals to cosine of the limit. So when we do cosine of the limit of n approaching infinity, 3 over n squared approaches to 0. Okay, the book does not write the intermediate step. So basically the two operations, limit and cosine, we can swap them. So limit of cosine equals the cosine of the limit. So when we take a limit of 3 over n squared, that's just 0. So cosine 0 is 1. Okay. So this, if we don't have math major, if you have math major, you have to know how to prove this. Why limit and cosine can swap. Okay. Squeeze theorem. So sometimes we learn the squeeze theorem for when we take limits, when we learn the limits, right? So very similarly here. If 3 sequences, right, one in the lower end, one in the upper end, and one is in the middle, if the lower end and the upper end converges to the same number, the squeeze, the forces the middle one to converge to the same number. So that's called squeeze theorem. Okay. All right, so we did this last time. So I'm going to, so now let's go to any questions? All right. If no questions, we're going to talk about infinite series. So let's see how much we have covered. So infinite series, divergence. So we have a couple of tests. Okay, we have divergence, integral test, comparison test, alternating test, ratio and roots test. Then in the end, we talk about power series. All right, so we have much more to cover. So I need to go to infinite series. So, okay, 5.21, explain the meaning of the sum of an infinite series to calculate the sum of geometric series. Remember, I have two types of typical series sequence. Now we're going to talk about the same thing, geometric series. Evaluate a telescoping series. We're going to learn what is a telescoping series. Okay, sums and the series. So an infinite series is a sum of infinite many terms and is written in the form, we just add up all this sequence, the first term, second term, third term in a sequence. We just add them up. But what does this mean? We cannot add an infinite number of terms in the same way we can add a finite number of terms. Instead, the value of an infinite series is defined in terms of the limit of partial sums. Okay, partial sums, because it's infinite, right? How can we add up an infinite many? No, there's no way. So what do? We just add a part of it, then we take a limit of it. We probably would add n of them, then we let n run to infinity. So a partial sum of an infinite series is a finite sum of the form, like this, right? So we just add k terms. So this sum is n from 1, so the subscript of a from 1 to k. So we just add a1, a2, a3 up to ak. So we just add up k terms. So then we take a limit of this sum, let k run into infinity. Let's see this example. To see how we use partial sum to evaluate the infinite series, consider the following example. Suppose oil is seeping into a lake such that 1,000 gallons enters the lake the first week. During the second week, an additional 5 gallons of oil enters the lake. The third week, 250 more gallons enters the lake. So we have 1,500, 250. You can see it reduced by 2. Assume this pattern continues, right? Assume the next one is half of 250, then half. Assume this pattern continues such that each week half as much oil enters the lake as did in the previous lake. If this continues forever, what can we say about the amount of oil in the lake? Will the amount of oil continue to get arbitrarily large, or is it possible that it approaches some finite amount? To answer this question, we look at the amount of oil in the lake after k weeks. So we use SK. SK means the summation of the k terms. Right? S1 just the first term. S2 is the first term plus the second term. S3 just add up the first 3 terms. S4 add up 4 terms. S5 add up 5 times. SK add up k times. So have this pattern 1 plus half plus quarter plus 1/8 plus 1/16, so on and so forth. We can use short notation. Summation of from 1 to k terms of half of n minus 1. Because our first term is 1, right? It's half raised by 0. Half raised by 0. So how do we make the exponent of half to be 0 first? Because n start with 1, so that has to be n minus 1. So 1 minus 1 will be 0. Half raised by 0, we get the first term. So the second term, we have half raised by 2 minus 1, so we get a half. And so on and so forth. So we are interested in what happens as k approaches to infinity, right? Because the question says, if this pattern continues, how much oil in the lake? Symbolically, the amount of oil in the lake as k approaching infinity is given by the limit, by the infinite series of this n from 1, the subscript n from 1 up to infinity, right? So this is a notation of infinite series. So this sum up infinite many terms. The short notation just from n goes from 1 up to infinity. That's how we write this summation sign. Anyone has question about summation sign? All right, keep going. At the same time, as k runs to infinity, the amount of oil in the lake can be calculated by evaluating limit k approaches infinity sk. So basically, we take a limit of this guy, this sum. Right, we take limit of this as n goes to infinity. And again, the limit and the summation sign can be swapped. So limit of summation equals to the summation of a limit, provided the limit exists. So evaluating the limit of sk approaches infinity. Therefore, the behavior of the infinite series can be determined by looking at the behavior of a sequence of partial sums. So if the sequence of partial sums converges, we see that the infinite series converges. Okay, that's the definition of infinite series converges. Before we talk about a sequence converges, right? Sequence converges. So which means, at a certain point, the sequence, the term in the sequence goes to a number. But here is a series converge. Remember, series means k terms, the sum of k terms. Okay, it's a sum of k terms. And its sum is given by limit k approaches infinity sk. Okay, sk means the sum of k terms in the sequence. If the sequence sk diverges, we see the infinite series diverges. We now turn our attention to determine the limit of the sequence sk. So we start with 1, then 1 plus half, so 2 terms. The sum of 2 terms is this 3 halves. Sum of 3 terms is 7 over 4. Sum of 4 terms, 15 over 8. Sum of 5 terms, 31 over 16. If we plot those points, have this, it appears the sequence could be approaching to 2, right? We could keep going. We could keep going at 6. We could try more. From this graph, it says, okay, it looks like, it's approaching to 2. Right. If sum of 5 terms, we get this much, 1.9375. Some 10 terms, we get this much. Some 15 terms, get this much. Some 20 terms, we get, approaching to 2. Looks like approaching to 2. Well, let's take a sequence. Let's go back here. Okay, let's see why we take it, because the book doesn't show. Let's see why we take it. So basically, we take the limit of this sequence, this summation. So when we take a limit, so k approaches infinity, summation, we can switch those operations. We put summation outside, we take a limit of a half raised by n minus 1, right? What's half raised by -1? That's 2, right? That's 2. So we get a limit of 2, and then the second part is a half raised by n. That's a 1 over 2 raised by n. What is the limit of 2 raised by n? So basically, we get the first term. In the rest of the term, we get half raised by n. So when we take a limit of that, of course, when k approaches infinity, that goes to 0, right? Because 1 over 2 raised by n. The denominator gets bigger and bigger, so the limit of this just 2. All right, limit of this just 2. But taking limit of this one, swap limit with the summation sign. Any questions about that? Or should I write on the whiteboard? Okay, so I think you understand me, right? Okay, all right. definition. The infinite series is an expression of the form, right? We add up infinite many terms, of course. For each positive integer k, the sum as k we call partial sums. So it's called the k partial sum of the infinite series. So the partial sums form a sequence sk. If the sequence of partial sums converges to a real number s, the infinite series converges. So this is a new definition. This is totally different from sequence, convergency of sequence. Convergency of sequence, remember in the weekly sign, we have a set of an, right? So an is one term. It's one term in the sequence. Now we have a sequence of what? Partial sums. We have a sequence of SKs. So each SK is considered as a term in the sequence, right? So this is different. And each SK is a partial sum of the infinite series. So if we can prove the sequence of partial sums converge to a real number, and then we can conclude the infinite series converges, right? Because k is arbitrary. And if we can describe the convergence of a series to S, we call S the sum of the series, right? So those are the definitions. So we come from the world of sequence, right? In a sequence, is each term. We have A1, A2, A3. That forms a sequence. But now when we talk about an infinite of series, the infinite series converges. We think about a sequence of partial sums. So we have to switch. We have to distinguish those two concepts. Wouldn't that make all series convergence? No, not at all, Zachariah. Think about, no, not at all. You will see soon. No. It's the same thing, not, you know. No. Okay, you'll see. So now we have, in infinite series, we have a sequence of partial sums. Okay, instead of have an before in the sequence, now we have sk. Okay, so each term in this sequence is a partial sum. It's a partial sum. You know, this takes a little bit of thinking. So if we can describe the convergence of a series to S, we call S the sum of the series, right? Because we call S the sum of the series, and we write like this. Okay, write like infinite series, right? And each term in the sequence we write as an equals to S. If the sequence of partial sums diverges, of course, we see the series diverges. We see some examples. Let's see some examples. Note that the index for a series need not begin with n equals 1, you know, but it can begin with any value. For example, the series n equals 1 up to infinity, we can write as a half of n minus 1. And also, maybe we can write as n starting from 0, right? So this is called a ray index. So n here is called an index. And from n equals to 1, we change it to n equals 0. We call ray index. So we can ray index, right? So this one, we start n with 1. That's half raised by n minus 1. Can be ray index n starting from 0, right? So n starts from 0, then n minus 1 becomes n. Right? N minus 1 becomes n. Because that one, in this one, upper one, we have 1 minus 1, 0. Half raised by 0 is 1. Here, n equals 0. Half raised by 0 equals 1. So this is called ray index. And also, of course, we can rewrite as n start with 5. If n start with 5, we write half raised by n minus 5. The first term will be half raised by 5 minus 5, which is half raised by 0, which is 1. Well, you can check the following terms too, right? If n equals 6, 6 minus 5, that's 1. So the second term is half. So this step is called reindex. We can always reindex. Let's see this one. This one we have n starting from 2 to infinity. We have 1 over n squared. Think of the first couple of terms. The first term will be 1 over 4. Second term will be 1 over 9. Then 1 over 16, 1 over 25, so on and so forth. Right? By introducing the variable m equals n minus 1, so we want to reindex this. So m equals n minus 1. So that means m starts with 1. Right? M equals n minus 1. So 2 minus 1 starts with 1. M equals 1, then n becomes, so m equals n minus 1, that means n equals m plus 1. Right? N equals m plus 1. So we can change n to be m plus 1 squared, 1 over that, 1 over m plus 1 squared. Reindex. Okay, normally we go from the bottom to the top. From the bottom to the top. But if we had m goes from 1 up to infinity, 1 over m plus 1 squared, we like to reindex, start from 2, and we have 1 over n squared. I think in your homework, you have reindex. Okay, anyone has any question? All right. Let's see this, evaluating limits of sequences of partial sums. For each of the following series, use a sequence of partial sums to determine whether the series converges or diverges. We'll take a limit of it. So the sequence of first one, A, so I have n over n plus 1, and n starts with 1. So we think 1 over 2, 2 over 3, 3 over 4, 4 over 5, so on and so forth. So partial sums, S1 will be half, S2 will be the first two terms, sum of the first two terms, S3 sum the three terms, S4 sum the four terms. So we keep going, we get a sequence of partial sums. So we see we get a half, 2 and a half, 2 times half, 3 times half, 4 times half, if we do this calculation. So we see the pattern. So for this pattern, we can see that as k is greater than k times half. You see S4 is greater than 4 times half. Because so when we add all this, yeah, the book didn't add all this. I choose to trust them. Okay, I don't want to calculate all this because we have to do common denominators, a lot of calculation. I don't want to do that. So basically, oh, we can think about this. 2/3, of course, greater than a half. 3/4 greater than a half. 4 over 5 greater than a half. That's why this whole thing greater than a half. So that means S4 is greater than 4 and a half. Right? So each SK is greater than k times half for each integer k. So therefore, SK is unbounded and consequently diverges. Right, we can see this keeps going. 4 times half, 5 times half, it keeps going. So going to infinity as k approaches infinity, and the partial sums approaches infinity. So that means it diverges. Okay. So therefore, the infinite series, n goes from 1 up to infinity, n over n plus 1 diverges. So it doesn't converge to a number. So let's see B. B is alternating 1, right? -1, +1, -1, +1. So we can add up some partial sums. So S1, the first one, S2, the first two, sum of the first two terms, S3, sum of the first three terms, S4, sum of the four terms, S5, sum of the five times. So we see a pattern. We see that's 1/2. I skipped B. Oh, sorry. Oh, yes. Yes, I skipped B. B is talking about alternating negative ones. So the first term is -1, second term is 0, because we have -1, +1, +1, -1. The third term is -1, the fourth term is 0, the fifth term would be -1, right? So basically it's jumping between 0 and -1. So for this pattern, we can see the sequence of partial sums is -1, 0, -1, 0, -1, 0, so on and so forth. So what does that mean? So if we take a limit of that, it's jumping from -1 and 0, -1 and 0. So it doesn't approach to a number. So that means it diverges. So that means the infinite series diverges, right? Because it's jumping between two numbers, 0 and -1, 0 and -1. So it does not approach into one certain number. So that's why the series, infinite series diverges, because the sequence of partial sums diverges. Any questions? What does it C? C is 1 over n times n plus 1. So starting from 1, so we have 1 over 1 times 2, 1/2. Then add the first two terms to get 2/3, 3/4, 4/5, 5/6. So we see the pattern: 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6. So for this pattern, we can see that the k's partial sum is given by k over k plus 1, right? You see the partial sum of 5 terms is 5 over 6. Partial sum of 4 is 4 over 5. Partial sum of 3 is 3 over 4. So as k equals to k over k plus 1. If we take a limit of this, the limit of the 1k approaches infinity, the limit of this approaches 1. So the limit of a partial sums, the limit of the sequence of partial sums approaches 1. That is to say, the infinite series converges to 1. So basically, we write this infinite series, n from 1 to infinity, of 1 over n times n plus 1 equals to 1. Any questions for this? All right, good, great. But let me repeat anyway. So we list from the given 1C, right, we list a couple of partial sums. So here we list like 5 partial sums, S1, S2, S3, right? So we observe a pattern, right? So it's n over n plus 1, right? So the first term is just 1 plus 1 plus 1. The second term is 2 over 2 plus 1. The third term is 3 over 3 plus 1, so on and so forth. That's why we're able to write it. So this step is crucial. So we're able to write in this form. We're able to write the case sum Okay, the sum of k terms. So don't confuse this with an. An is just one term. Right? An is one term. Sk is the sum of k terms. Sum of k terms. So when we take a limit of this, that goes to 1. So we conclude, because of partial sums, the limit of partial sums goes to 1. That's why the infinite series converges to 1. So we write as this. The infinite series equals to 1. All right, you try 5.7. So we have infinite series of n plus 1 over n, starting from 1. Looks like it converts to 0. Prove it. Prove it. Write out a couple of partial sums. What do you, Ali, what do you mean n plus 1 over n? Yeah, okay. We have to shift from the sequence of every term to partial sums. So my suggestion is to list a couple of partial sums to get a feel of it. Yeah, Shahara, yeah, I think your intuition is same as my intuition. Just prove it. Yeah, SK equals to 2, S2 equals to 3 halves. No, S2 doesn't equal to Okay, Damon, you're calculating each term. You should calculate each sum. So S1 equals to 2. Okay, let me read some of my calculations. S1 equals to 2. S2 equals to 3/2 or 7/2. S3 equals to 29/6. And S4 equals to 5/4 plus 26/9. 73/12, which is about 6.5. I can keep going, right? I see the number gets bigger and bigger. So that means when k approaches infinity, and this approaches infinity, because the number goes bigger and bigger. So this series diverges. Okay, the famous harmonic series. So 1/n, right? It's called harmonic series, very famous sequence. And it diverges, it doesn't converge, right? You see the sequence itself converges to 0, right? Because when the denominator n gets bigger and bigger, 1/infinity, that goes to 0. So that means when n approaches infinity, and the sequence itself converges to 0, but not the partial sums. Not the partial sums. Let's see this. If we add up 10 terms, we get about 2.9 something. If we add up 100 terms, we get 5.18. 1,000 terms, we get 7 something. 10,000 terms, 9 something. 100,000 terms, 12. So it's a number keeps going bigger. So after 1 million terms, the partial sum is still relatively small. For this table, it's not clear that this series actually diverges. It diverges. To show that the sequence of partial sum diverges, we show that the sequence of partial sum is unbounded. So we begin by writing the first several partial sums. So we always do this, because when we read a couple of partial sums, we get some intuition, get some feeling about it. S1 equals 1, S2 equals to 1 plus half, right? 3/2, so on and so forth. We could see the partial sums gets bigger and bigger. Here says, notice that for last two terms in S4, so 1/3 plus 1/4 is greater than 1/4 plus 1/4. So what do? So S4 is greater than 1 plus half plus quarter, okay, which means we can write it as a 1 plus 2/2. All right, so now we can write as general term, I guess. So S8 can be written as S8 is greater than 1 plus 3 times half. So we could see S16 probably greater than 1 plus 4 times half. So in general, S of 2 raised by J, right? We see this is a 2 raised by 1, 2 raised by 2, 2 raised by 3, where S16 will be 2 raised by 4. So that means the partial sums of 2 raised by J terms is greater than 1 plus J times half for all J greater than 1. But since 1 plus J times half approaches infinity, so we conclude the partial sums, it goes to infinity. It's unbounded or diverges. Right? So this is like one of the tricks how to prove this. But a harmonic series is a famous series. It's a famous diverging series. Harmonic series has many applications. It's a divergent series. right? Even the sequence, even the term in the sequence seems goes approaching infinity, converges, right? But the series is a divergent series. Okay, anyone has any questions? Okay, let's keep moving. Oh, by the way, I upload the answers for exam 2. So I do hope you have time to review it, all right, to study it. Because even final exam will have part of the exams, part of the questions. Oh, you're welcome. Okay, theorem, algebraic properties of a convergent series. So let's see, we have those two convergent series. One is Bn, one is An. And the following properties hold. Summation of the series is a summation. All right, because remember, if it's convergent, right? If you series convergent, it converges to a number. So any property applies to real number, it would apply to this. So let's just forget about this. So let's see this one. Use the algebraic property of a convergent series. Evaluate this. Excuse me. So you see here we have two series, right? We have 3 over n times n plus 1. And second one, we have a half of n minus 1. You know, what do we want to do? We want to break into two series, right? So this is a series of a summation. This is a series of summation. By the property, we can break it into summation of two series. So we break into summation of two series. The first one we already say equals to 1. The infinite series equals to 1. And the second one we also say in the previous examples we get 2, right? Because what's half raised by -1? Half raised by -1, that's 2. So the first term is 2. And the rest of the term is a half raised by n. Then we'll take a limit of, n goes to from 2 up to certain k, then let it, or we could just go to infinity, right? So half raised by n, that goes to 0. So the limit of this is 2. So then the summation of this, so the series of a summation of these two just equals the summation of the two series. So we just add 1 with 2, we get 3. Okay. So the summation of those two is just 3. Okay. Oh, hold on a second. The original question is this. Oh, the original question is 3 over n times n plus 1. All right. 3 is a constant number. 3 is a constant number. So 1. We can just pull 3 out of the summation sign. So the limit of first part equals to 3. And the second part is n minus 2 instead of n minus 1. So half raised by -2, that's 4. So 3 plus 4 is 7. But Paul, 3 plus 1 plus 2, yeah, you're almost right. You're almost right. Because it's tricky. Here we have n minus 2, not n minus 1. N minus 2 means the first term is a half raised by -half, which is a 4. So 3 plus 4, 7. So we break into two series, right? The first one, we can factor out 3 outside the summation sign, which will have 1 over n times n plus 1. We know that goes to 1. And the second one, we can pull half of raised by -1 up front, we'll get 2. Then the rest of this one, we know it goes to 2. So 2 times 2, that's 4. So we get 7. All right, anyone has any questions? I see. Let's see. We have 22. Oh, someone is reconnecting. All right. So no one has questions? I thought those are difficult objects. All right, let's keep moving. Okay, everyone try 5.8. If you have no questions, I expect everyone give me an answer for this, please. You only need to prove for the first term. Damon, what do you mean by that? Are you talking about the first one? Are you talking about this example? Okay, let's wait. I thought this is difficult to understand. Okay, let's see. So we have this series. So this series is a summation, right? This series itself is a summation of two terms. So what do? We split it into two series, right? Because we have knowledge of this, we proved this before, previously, and we know this before, previously. So we just use those two to break the series into two. I mean, first n equals to 1. Okay, so your question is talking about which one? So we have two series. I talking about the first one? Yeah.
Yeah, right there at the bottom where you have, we conclude that the summation from n to infinity, you're only proving for the n equals 1 I see on the right side of the screen, where it shows negative
Right.
1, where it's
Yeah.
raised to negative 1.
Right.
So you only need to prove for the first n equals 1 to solve the problem?
Yeah, we're using, so this part we have proved before.
Mm-hmm.
This part we see, this one, I don't want to highlight the first one. So this one, so summation n goes from 1 up to infinity, half raised by n minus 1. This part we proved is 2 before, right?
But where did that the first half
Oh, this scalar, half raised by negative 1.
yes, where did that come from?
Okay, come from here. You see, this term is n minus 2.
So you're
See that?
only proving for n equals 1 there. Because n minus 2 would equal negative 1.
Oh, that's right. Okay, I see where you're coming from. So that's from, all right, let me go to whiteboard. Let me go to whiteboard. So this one, n goes from 1 up to infinity. And the inside we have half n minus 2. I think you're thinking, okay,
Mm-hmm.
n goes from 1, n minus 2 is negative 1, right?
Mm-hmm. Mm-hmm.
That's okay. Let's see why. What's half raised by negative 1?
2.
2, right. That's just a way of writing it. So in reality, this is just a 4. N goes from 1 up to infinity. half raised by n. I could write n here, right?
Okay.
You see this?
Mm-hmm.
Right. If we take a limit of this, well, let's not take a limit of this because we have done this part already. So let's follow the book. The book did is 2, and this is n minus 1 instead of just n, right? So the book proved this part is 2. Then 2 times 2, that's 4. Does this answer your question?
So what I meant is that basically you only have to prove for n equals 1, right?
Oh, this index, yes. But for this one, we just want to use this, you know, for a 2 as a 2, because this is being proved. But in general, you can start n with any number. That's about a rate
Okay.
index.
Okay.
Yeah.
All right. Thank you. Okay.
You're welcome. You're welcome. Okay. Any other questions? All right. Let's keep going. So under the summation sign, the index, we can always reindex. So n starting from 1 or n starting from 0, n starting from 2, that's called a reindex. It depends on, you know, what we want them to be. For this case, we want to use the previous one we proved. So previously we have proved this. So we want to use this as a fact. All right, let's all try 5.8. Conversion, so does this just converge to 5? You're right. You're also using the previous one, right? Oh yes, 10 should be 10, right? Because 1 over 2 raised by n minus 1 converges to 2. So 2 times 5, that's 10, right? Paul, you have to multiply 2 with 5, right? Damon was right. 10. Shahaya, yes. 10, 10. Yeah, it's 10. So this is a used previous one. What about the rest of you being so silent? Does this make sense? Do we need to reindex the 2? No, we don't need to reindex this. We don't need to reindex. We just use this one as a 2. We just use this one. Just use this one. You see this one index from n equals 1. Half raised by n minus 1. It's the same as 1 over 2 raised by n minus 1. So we just use this one as a 2. And the 5, we see 5 is a scalar, right? This 5, we can put out the summation sign. We can write as 5 summation sign 1 over 2 raised by n minus 1. Yes, it's 10. All right, Jeff, where did we get 5 times 10 from? All right. Oh, okay, you understand now. Great. wouldn't it be half 1 over 2 raised by 1 minus 1, which is 1 over 2 raised by 0? Oh, you're right. Right. Okay, hold on. I'm making mistake. So now this is 2 raised by n minus 1. Oh, no. No, Reggie. Who is talking about this? No, Paul. What is 1 over 2 raised by negative 1? Oh, you were saying, okay. You were saying if I calculated the first one, I would get, that's 2, yeah. Yeah. It's 1 plus half plus quarter. You're right. Yeah. Yes. Yeah. Just remember this famous series. Why is it negative 1 if it's 1 minus 1? So n start with 1. We have 1 over 2. Yeah, okay. Let's go back to the book. So we have 1 over. Okay, this one is a little bit different. This one is not, we cannot use this one. We cannot use this one. Okay, that's the tricky part. I think that might be a typo. This might be a typo, but anyway, we see those two are different. Let's go to the right. Let's go to the whiteboard. I know exactly what you mean now. Let's try this one. So that is, okay, n minus 1 in the denominator. Okay, let's try this together. Let's see your comments first. Right, you're right. Let's do this together. So we cannot, it might have type O in it. Okay, first, half raised by n minus 1 is different from 1 raised by 1 over 2 raised by n minus 1, right? Oh, no, it's the same. Isn't it the same? Actually, no, because 1 over n minus 1 would always, 1 over 2 raised by n minus 1 would always equal to 1, so it still applies. Well, let's see. So this one we can write as a half. Yeah, that's true. Then 1 over 2 raised by n. Yeah, that's the same. They're the same. So those two exactly the same, right? Those two equal each other. Basically, we have half raised by negative 1, which is 2. 1 over 2 raised by n. 2 raised by negative 1. That's 2. Yeah, so the only tricky part is this. What is the first term? So we're trying to figure out the first term here. We have 1 over 2 raised by n minus 1, right? So this one can be written, yeah, you help me out. So this is tricky. So we can write this one as 2 times 1 over 2 raised by n, right? So if we substitute 1 from it, the first term will be 1. The first term will be 1. And we want this to get 2. So it would be the same as half raised by n minus 1 times right. Yeah. So those two exactly the same. Those two exactly the same. Because 1 raised by n minus 1 is still 1. 1 raised by anything is still 1. So we're only left with 2 raised by n minus 1. The question is this. The question is, what's the difference between this series and this series? Right? If we, so this one, if we figure out, so if we plug in 1 to this one, right? So n minus 1 will be 1 minus 1. 2 is raised by 0. That will be 1. 1 over 1, that will be 1. So that's saying the first term is 1. Oh, okay. So here, it is 1 also, just in different writing, right? Just in different writing. So this one is saying, I put 2, 1 over 2 raised by negative 1, that's 2. So the first term is still 1, because 1 over 2 raised by 1, that's 1 half. 1 half times 2 is still 1. Still 1. Let's see. Let's go back to the book. Let's go back to the textbook. Okay, they're exactly the same. Let's go back to the book to see the proof. Prove that equals 2. Okay, here. Let me see your comments. Half raised by n minus 1 is the same as 1 over 2 raised by n minus 1. You're right. You're right. Let's see the proof. Why that's 2. Here. Okay, we got it. So this is by so how do we write SK term? So K terms. Okay, so SK can be written in this term. So that's, so we take a limit of SK, let K run to infinity. So limit of this, we can write as 2 times 1 over 2 raised by n, right? So this is saying, so take a limit of SK sequence. Oh, okay. The data supply more evidence suggesting that the sequence SK converges to 2. Okay. So it's not by proving taking the sequence. Because if we take a sequence, it doesn't tell us 2. It tells us it's 1. So this is by analysis. Okay, so this is by analysis. So the book is saying later we will provide an analytic argument that can be used to prove that. Okay, so later on we'll see the proof. So now just just let us take this as a fact. So limit of this, I mean this sequence, this series, so this series converges to 2. Okay, so we will see the proof, a solid proof later on. It's not by directly prove by taking the limit, because if we take a limit, we wouldn't get 2. So for now, just for us, just try to remember this as a fact. as a fact. All right, so no more argument on that. So now we can go back to our question. Okay, this one. So we'll come back to this one. So right, so that's how we got 10. So we take, you know, take 1 over 2 raised by n minus 1, you know, converges to 2. Then 5 is a scalar of this summation. So 5 can be pulled out of the summation sign. So 5 multiplied by 2, we get 10. Okay, anyone has a question about that, about 5.8, how we got 10? Okay, let's keep moving. Geometric series. All right, we see this common ratio R. Getting cold. So we see the first term A plus AR plus AR squared plus AR cubed. We factor out A. We have 1 plus R squared plus R cubed, so on and so forth. Basically, we're just writing summation sign. Let n goes to 1 up to infinity. Excuse me. So A times R raised by n minus 1. Thank you. Because the first one is 8, right? It's 8. So that's why the exponents of R is n minus 1. So that gives us the first term to be 8. Now we see the proof. Okay, I think we're getting to the proof of this one. So summation sign of n goes from 1 up to infinity, half raised by n minus 1. We see that's 1 plus half plus 1/4 plus 1/8. So the ratio R is half. So geometric series, right? So this is a geometric series with the initial term A equals 1. Okay, initial term. So in geometric series, initial term is important. It's 8. A equals 1, and the ratio R equals to half. Ratio R equals to half. In general, when does a geometric series converge? Consider geometric series when R is less than 1, because R here is half. And A, when the first term greater than 0, okay, so it's a sequence of partial sums as K is given by this form. A plus AR plus A squared, blah, 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 plus AR to the K minus 1 term. So SK equals A plus A1 plus A1 squared. Oh, if R equals 1. If R equals 1, right? If R equals 1, we get A times K, of course, because 1 raised by anything. 1 raised by anything will be 1. So we have a K of A's adds up. That's AK. Since A is positive, we know AK goes to infinity as K goes to infinity. So what does that mean? That means if R equals 1 or greater than 1, the sequence is unbound. Then the series diverges. So this ratio R, if it equals to 1 or greater than 1, the series diverges. Now, it's saying, okay, let's think about 1 minus R as K. Let's multiply 1 minus R on both sides. Remember, 1 minus R times 1 plus R, to R to the K minus 1. This is 1 minus R raised by K, right? Think about difference of two squares. If we have A squared minus B squared, that's A plus B times A minus B, right? If we have 1 minus R squared, that's 1 minus R times 1 plus R. If we have 1 minus R cubed, the difference of two cubes, we have 1 minus r times 1 squared plus 1 times r plus r squared, which is 1 plus r squared. So on and so forth. So we get, so 1 minus r times 1 plus r up to r raised by k minus 1 give us 1 minus r raised by k. Now we can divide 1 minus r on both sides. So we get sk equals a times 1 minus r raised by k divided by 1 minus r. Of course, for r not equal to 1. Because if for r equals to 1, we know the series diverges, right? Which is quit from there. If r is greater than 1, the series diverges, which is quit from there. So we're trying now to find r is less than 1. So from our discussion in the previous section, we know that geometric sequence rk goes to 0 if absolute value of r is less than 1. Okay, absolute value of r is less than 1. And that r raised by k diverges if absolute value of r is greater than 1, yeah, or equal to 1. So therefore, when the absolute value of r less than 1, sk, the sum of k terms, equals to a divides 1 minus r. Okay, so this is the formula. So this is a geometric series. This is the formula for geometric series when the ratio is less than 1, when the absolute value of the ratio, because the ratio can be negative, right? When the absolute value of the ratio less than 1. So that's how we get that one equals to 2. Okay, now let's go back to that example. Yeah, this one. So the first term is 1. So we get 1 over 1 minus ratio, which is 1 minus half. So we get 1 over 1 minus half. Well, 1 minus half is half. 1 over 1 half, which is 1 divided by half, which is 2. So that's a geometric series. That's the formula for find the limit of the geometric series, which is when r, when the absolute value of the ratio is less than 1, we have this formula that equals the initial term divides 1 subtract the ratio. All right, so this is important. So geometric series, if the ratio, absolute value of the ratio is less than 1, the infinite series converges to initial term divides by 1 minus the ratio. That's how we got the 2 for the previous one, because the initial value is 1, the ratio is half, so get 2. Anyone has any questions? Okay, let's see some examples. Okay, so this is the definition. A geometric series is a series of the form this, okay? AR squared, AR cubed, so on and so forth. When the absolute value of the ratio is less than 1, the series converges, and it converges to the initial value divides by 1 minus the ratio. And if the ratio, absolute value of the ratio is greater than or equal to 1, the series diverges. Okay, this is very useful. Let's see this one. So this one we have n goes from 0 up to infinity, and 2 over 3 n plus 2. Okay. So we could figure out the initial value, the first term. So what's the first term? First term is 4 over 9. Okay. N starts from 0, 0 plus 2 is 2. So 2 over 3 raised by 2, that's 4 over 9. So A equals to 4 over 9. And the 4 over 9 divided by 1 minus 2 over 3. First, we can conclude, first, we see this geometric series converges because the ratio is 2 over 3 is less than 1. And then we see it converges to the formula. Initial term is 4 over 9 divided by 1 minus 2 over 3. 1 minus 2 over 3 is 1/3. 4 over 9 divides 1 over 3. That's 4 over 3, right? So it converges to 4 over 3. Yeah, if we read out some terms, we get 3 over 2 squared, 2 over 3 squared, 2 over 3 cubed, so on and so forth. So the first term, we need to figure out the first term. Right? First term is 4 over 9. The ratio is 2 over 3. Then we just substitute into the formula, right? So 4 over 9 divided by 1 minus 2 over 3, which is 4 over 3. Okay, anyone has any questions? All right, let's keep moving. So let's see these examples, right? Determine convergency, divergency of the geometric sequence. Let's see 8. The denominator will have 4 raised by n minus 1. The numerator will have -3 raised by n plus 1. And b is e raised by 2n. The second one, obviously, right? Obviously diverges. Let's see the first one. The first one we have hope, because we see 3 over 4. Right? So if we read out some terms, we get this. We get -3 squared over 4 raised by 0. Because n start from 1, we just substitute 1 into the first term, second term, third term. So we simplify a little bit. We see -3 squared, -3 squared multiplied by -3 raised by 4, -3 squared multiplied by -3 raised over 4 squared, so on and so forth. So we see -3 over 4 is a ratio R, right? Absolute value of that less than 1. Okay, we know this geometric series converges. So when you figure out the first term is just -3 squared, which is 9. So we use the formula, the first term, 9, divided by 1 minus the ratio. The ratio is -3 over 4. So that becomes 1 plus 3 over 4. So we get 9 over 7 over 4, which is 36 over 7. So we just use the formula. We'll figure out the ratio, the first term, then we use the formula. Any questions? All right, second one, we can rewrite this one. So we see the ratio is E squared. The E squared, E is Euler number, is 2.712. A goes on forever, it's just like a pi. And of course, it's greater than 1. So the series diverges. And then this one converges, right? By intuition, we know this one converges. So you can try it on your own. Let's see this one. Write repeating decimals as fractions of integers. So we have 3.26 bar. That means the number is 3.26, 26, 26, 26, goes on forever. So we can write this series as 3 plus 26 over 100 and over 10,000, so on and so forth. So we rewrite that. We see the denominator is 10 squared, 10 raised by 4, 10 raised by 6. And the numerator doesn't change. The numerator stays to be 26. Right? So we see the ratio. So the first term, why this is seen in the first term? Okay, So basically, and say, forget about 3, right? Forget about the term 3, because the term 3 has nothing to do with the rest of the terms. So starting from the second term, we see a pattern. We see ratio is 1/10 squared. Ratio is 1/10 squared. And then A, just the first term, 26/10 squared, over 100. So we use a formula, 26/100 minus, divided by 1 minus 1/100. We do that at 26/99. Then we cannot forget about this 3, right? Because we ignore this 3. Because 3 doesn't follow the pattern for the rest. So we just leave the 3. Then when we figure out the rest of it converges to 26/99, we just add 3 to it. We just add 3 to 26/99, so we get 323/99. All right. So it's about figuring out the pattern, figuring out the R, the ratio R. Okay, we're not going to do this. Telescoping series. We don't have time to do that today. We'll do this next time. All right. Anybody has any comments? Any questions? Let me take a picture of the attendance. There were 22 of us, so someone left early, I guess. Right, someone left. Who was that? I forgot. I didn't take a picture in the beginning. Kelly. Oh, I see. Okay, again, some of you in class are very silent, and among you guys, some of you did well for the midterm exam, but some of you, did not do very well, and makes me worry. In the end of this course, I won't be able to allow you to pass. So tell me, how I can help you. And yeah, I know you want to pass, but the only thing to pass this course is yourself, right? You show me you can pass. Yeah, tell me if I can be any help. And for you, you really have to tell me if you understand me or not. And typically in class time, right? If you have questions, if I don't make sense to you, please let me know. Otherwise, I'll just keep murmuring along. Yeah, I don't know. Okay, let's see your comments. B. Xinxin, I just want to know, do we have another exam before the final exam? No, we don't. We only have 2 exams. And we only have 2 exams. So the final exam will have questions from the midterm, okay, from the material. The final exam covers everything. And also the final exam, I think worth 40, right? Worth 40. But if you can show me you understand everything in the final, I have no problem to bump up your grades. All right. The final exam going to be curved. The final exam, Jack, to answer your question, first, I'm not going to trust the textbook. I'm still going to, extract questions from out of the textbook, but I'm going to do myself first this time to make sure every question makes sense, no typo in it, all right? So that's my job. And then I'm not sure if it's going to be curved, right? Maybe the final, I give you less questions, all right? Less questions to focus on important things. What else? What else? I just hope, and typically, you know, students, if you are here, you know, you're not participating and then you're hoping to pass this course, that just doesn't make any sense. They don't even mention students always absent from this class. And I don't know, you know, I know some students get 10 points, which I feel bad to give 10 points. So lowest grade, I made 50. So it's like as long as you participated in midterm, your lowest grade is 50. But the 50 is just to comfort you, all right? In reality, some of us only get 10 points, 20 points, 30 points. I felt really bad. I felt like, you know, man, I did not make any sense to them. I basically feel I failed. Okay, sorry, I went over. I don't want to take any of your time. Your time is precious. Go study hard. If you have any questions, please ask. All right. Thank you very much. Good night. Good night. Okay, for a lot of you, keep your good work. Okay, keep working on it.